In the vast ocean of the cosmos, where galaxies drift silently like ships across an endless void, stars are born, live, and die in cycles that span billions of years. Among countless suns, most lead quiet lives, their brilliance unnoticed in the grand architecture of the universe. But occasionally, a star's fate intersects with forces so immense that its story becomes extraordinary, a narrative that stretches across space and time. This is the story of such a star, one that would confront the most extreme force in existence, a black hole, and yet, in defiance of inevitability, escape at a speed almost beyond imagination, 8 million kilometers per hour. Black holes are not merely voids. They are regions where gravity concentrates with unimaginable intensity, where matter and energy succumb to forces that warp the very fabric of space and time. They emerge from the collapse of massive stars or the slow accretion of cosmic matter over billions of years, forming singularities where density approaches infinity. Surrounding each singularity is the event horizon, a boundary beyond which nothing can return. To cross this threshold is to disappear from the observable universe, to be erased from reality as we know it. Yet, even in this dominion of seemingly absolute power, exceptions can occur, and the universe allows moments of extraordinary defiance. For millions of years, this particular star had burned steadily, a beacon in its galactic neighborhood. Its orbiting planets danced in harmony, warmed by the steady pulse of its energy. Life, if it existed on any of these worlds, would have thrived under its light, carried along by the rhythm of cosmic stability. Its existence was unremarkable, predictable, and constant. But the galaxy is never truly static. Over time, gravitational nudges, interactions with neighboring stars, and the subtle pull of unseen dark matter shifted the star's path, nudging it toward a region dominated by a supermassive black hole. The gravitational attraction was imperceptible at first, a whisper across light years, but persistent, bending the star's trajectory until it was drawn inexorably toward the ultimate cosmic predator. As the star approached the black hole, the universe revealed its extremes. Space itself stretched, light bent in unnatural arcs, and time slowed near the event horizon. The star began to experience tidal forces of extraordinary magnitude, gravitational differentials that pulled its near side with one force and its far side with another. Its shape elongated into a filament of incandescent plasma, glowing as gravity attempted to tear it apart. Streams of stellar materials spiraled inward, caught in the gravitational grip, while the core endured pressures so extreme that any known substance would have been crushed instantly. To distant observers, the star's transformation appeared both terrifying and mesmerizing, a thread of fire suspended against the black void, writhing in the jaws of annihilation. Normally, the outcome of such a close encounter is total destruction. The star is shredded, assimilated into the black hole's accretion disk, leaving no trace of its prior existence. Yet, in this case, the star's internal dynamics reacted in a way that would become unprecedented. The compression of the core under immense tidal stress triggered an extraordinary surge of nuclear fusion. Reactions accelerated beyond ordinary stellar limits, producing an energy release so intense that it began to counter the gravitational pull. The outer layers, heated to extraordinary temperatures, were expelled in powerful jets along the star's rotational axis, creating a spectacle of plasma and radiation that defied the boundaries of expectation. At this moment, the star's fragments were propelled outward at unimaginable speeds, 8 million kilometers per hour. The expelled matter became a streak of light slicing through space, racing away from the black hole's grasp, carrying with it not only mass, but information about the forces that had nearly destroyed it. Radiation across the spectrum, from gamma rays to visible light, was emitted in torrents, illuminating the star's violent escape for observatories across the galaxy. For astrophysicists, it was an unprecedented opportunity, a live demonstration of extreme gravity, nuclear physics, and relativistic motion, all intertwined in a cosmic ballet that defied human comprehension. The implications were profound. The interaction between gravity, nuclear fusion, and angular momentum demonstrated the complex dynamics that govern stellar behavior near black holes. The escaping plasma carried momentum and energy, interacting with interstellar magnetic fields and matter, creating shockwaves and luminous filaments that painted the cosmos with transient beauty. Each photon emitted during the escape was a messenger, a carrier of information about the extraordinary forces at play, a story written in light and energy across unimaginable distances. Even now, as the star's remnants travel across interstellar space, their influence continues. They may collide with molecular clouds, triggering new star formation, or interact with distant planetary systems, injecting energy and matter that could shape the development of future stars. In this way, the escape was not merely survival. It was the beginning of a new journey, one that would reverberate across the galaxy for eons to come. The universe, in its vast complexity, allowed a fragment of matter to survive, to shine, and to continue influencing the cosmos in ways that could not have been predicted. As the star approached the event horizon, the forces acting upon it became almost unimaginable. The tidal gravity stretched the star into a needle-like shape, pulling its outer layers toward the black hole while compressing its core under inconceivable pressure. Within that core, nuclear fusion accelerated to extremes far beyond its normal stellar processes. At this threshold of destruction, the star's interior became a furnace hotter than the surface of most stars, a searing crucible where hydrogen and helium fused at unprecedented rates, releasing energy that defied the immense gravitational grip of the black hole. The reactions were violent yet exquisitely directed. Energy radiated along the rotational axis of the star, forming narrow, powerful plasma jets. These jets acted almost like cosmic cannons, propelling the outer layers away at astonishing velocities. Accelerated by a combination of relativistic effects, nuclear energy, and the black hole's gravitational influence, fragments of plasma tore through space at 8 million kilometers per hour. Each jet emitted high-energy radiation, gamma rays, X-rays, and ultraviolet light, that radiated across millions of kilometers, creating a transient halo of brilliant luminosity around the escaping fragments. Observatories across the galaxy detected the phenomenon almost simultaneously. Satellites and ground-based telescopes recorded bursts of high-energy radiation that defied conventional models of stellar activity. The jets were not only moving at incredible velocities, they were transporting matter with precise directionality, a testament to the extraordinary physics governing the star's escape. Astrophysicists immediately realized they were witnessing a once-in-a-lifetime event, an interaction between a star and a black hole so extreme that it pushed the boundaries of known science. Every photon captured was a clue, a piece of the puzzle that could illuminate the hidden processes of the cosmos. The plasma streams interacted with the surrounding interstellar medium in dramatic fashion. As the fast-moving fragments collided with diffuse clouds of gas and dust, they generated shock waves that illuminated the void, producing arcs of ionized material that glowed across the spectrum. Some fragments ignited pockets of gas, compressing them enough to trigger localized nuclear reactions that would eventually form new stars. Others were deflected by gravitational interactions with nearby stars, altering their trajectory and seeding energy into regions of space that might otherwise have remained dark. The escaped material had become both a survivor and a catalyst, transforming destruction into creation. Simulations of the event revealed even more astonishing details. The star's core, though ultimately consumed by the black hole, had contributed significantly to the energy of the escape. The interplay of rotational momentum, internal pressure, and gravitational stress produced a perfectly timed release of energy. The plasma jets were not random. They were guided by the physics of the star's collapse and the curvature of spacetime near the black hole. This rare alignment allowed a portion of the star to survive and escape at velocities that no human technology could ever replicate, a cosmic miracle occurring at scales and speeds incomprehensible to the human mind. As the fragments raced away, they left behind traces of their journey that could be measured across vast distances. Electromagnetic signals carried information about the composition, density, and energy of the expelled plasma. By analyzing these signals, astronomers could reconstruct the event in unprecedented detail. The star's escape provided insights into tidal disruption events, relativistic jet formation, and the limits of matter under extreme gravitational forces. It offered a natural laboratory for the study of high-energy astrophysics, one that could not be recreated in any earthbound experiment. From a human perspective, the spectacle was awe-inspiring. Scientists marveled at the data streaming from observatories, while simulations projected the star's path across space in vivid detail. Visualizations depicted the glowing plasma jets threading through interstellar gas clouds, bending under gravitational fields and forming luminous arcs that stretched for millions of kilometers. The escaping material carved a transient path of brilliance through the darkness, a blazing testament to the interplay of energy, matter, and the relentless forces of the universe. Philosophically, the event carried profound meaning. In a region dominated by overwhelming gravitational forces, where the star should have been obliterated without trace, fragments persisted, traveling across the galaxy as a symbol of cosmic resilience. It was a reminder that even in the most hostile conditions, matter and energy can survive, adapt, and continue their journey. The universe, it seemed, allowed for exceptions, moments where defiance against the inevitable was not only possible, but spectacular. As the plasma jets moved farther from the black hole, their interactions with interstellar matter became more complex. Magnetic fields twisted and redirected portions of the streams, creating spirals of charged particles that radiated energy across multiple wavelengths. Dust and gas clouds encountered by the fragments were compressed and heated, generating secondary emissions visible even from thousands of light years away. In effect, the star's escape became a traveling spectacle, leaving a trail of energy and matter that transformed its surroundings. The escaping fragments carried signatures of the star's original composition. Heavy elements formed over millions of years within the star's core were distributed into the galaxy, enriching the interstellar medium. This process of chemical seeding is critical in cosmic evolution, as it provides the building blocks for future stars, planets, and potentially life itself. In this way, the star's survival did more than preserve energy. It contributed to the ongoing cycle of creation in the galaxy. For astronomers, the event was a window into extreme astrophysics. Every measurement of velocity, radiation intensity, jet composition, and trajectory offered insights into relativistic physics and stellar dynamics. The star's interaction with the black hole provided data on space-time curvature, the behavior of matter under tidal stresses, and the limits of nuclear energy release. By analyzing these observations, scientists refined models of black hole-star interactions, enhancing our understanding of the most violent and mysterious objects in the universe. Even as billions of years pass, the fragments will continue to traverse interstellar space. Some may eventually collide with other stars, planets, or gas clouds, injecting energy and matter that shape the evolution of distant systems. Others will travel nearly untouched, silent witnesses to the extraordinary forces that propelled them. The star's legacy, therefore, is not confined to a single moment of escape. It extends across eons, influencing the structure and chemistry of the galaxy long after the initial event. The narrative of the escaped star also highlights the dynamic interplay between light, energy, and matter. Each particle carries kinetic energy and electromagnetic information, interacting with cosmic structures and producing observable phenomena. Gamma rays, X-rays, and visible light from the plasma jets illuminate previously dark regions of space, allowing observers to trace the star's journey. The energy deposited in interstellar clouds can ignite new star formation or modify magnetic fields, demonstrating how a single event near a black hole can have repercussions across astronomical scales. In sum, the escape of the star was both a scientific marvel and a cosmic narrative of resilience. It defied expectation, challenged physics, and left an indelible mark on the universe. It reminds us that even in regions dominated by forces of annihilation, energy and matter can persist, creating ripples of light, matter, and chemical enrichment that echo across galaxies. The 8 million km/h escape is a testament to the extraordinary power of the cosmos and the capacity for matter to endure even against the most extreme odds. As the star's fragments streaked away from the black hole, they entered the vast, dark expanse of interstellar space, traveling at a speed incomprehensible to human imagination, 8 million km/h. At such velocities, the distance from one star to another, which normally spans light years, could be crossed in a fraction of cosmic time. The fragments carried not only mass, but also information encoded in energy, radiation, and motion, a testament to the extraordinary forces that had nearly destroyed them. Each particle became a messenger, traversing the galaxy with a story written in light. The journey was not solitary. Interstellar space, while often depicted as empty, is rich with matter, magnetic fields, and radiation. Clouds of hydrogen and helium, the remnants of ancient supernovae, lay in the path of the escaping material. As fragments collided with these clouds, they transferred energy, compressing gas and dust, and triggering localized heating. In some regions, this compression was enough to initiate new nuclear reactions, planting the seeds for star formation millions or even billions of years into the future. The star's fragments had become agents of creation, transforming destruction into life in the silent reaches of space. Magnetic fields added another layer of complexity. The galaxy is threaded with invisible lines of magnetic force, which bend and twist under the motion of charged particles. The plasma expelled from the star, ionized and highly energetic, interacted dynamically with these fields. Spirals formed as particles followed the curvature of the lines, producing radiant arcs and glowing filaments that illuminated the darkness. In effect, the escaped star was painting the galaxy with ephemeral strokes of energy, leaving behind a visual record of its extraordinary journey. Radiation emitted by the fragments traveled far ahead of the physical material, lighting the path for distant observers. Gamma rays, X-rays, and visible light propagated across vast distances, creating a luminous trail detectable by sensitive instruments. Astronomers, whether observing from space telescopes or remote observatories, could reconstruct the star's trajectory, measuring its speed, mass, and energy output with astonishing precision. The star had become a natural experiment, providing humanity with insights into the behavior of matter under extreme gravitational and nuclear conditions. Over millennia, the fragments continued to traverse interstellar space, weaving through the gravitational fields of nearby stars and planets. Some fragments were deflected slightly, altering their paths and creating a complex pattern of motion that stretched across the galaxy. The journey became not only a physical migration, but also a demonstration of the intricate dance between gravity, inertia, and energy. Even as time passed, the story of the star persisted, written in motion, light, and radiation, visible to any who had the knowledge and instruments to observe it. As the fragments entered regions dense with nebulae, vast clouds of gas and dust, they interacted with their environment in remarkable ways. Shock waves generated by high-speed collisions compressed sections of the nebula, heating the material and causing it to glow with radiant intensity. Ionized particles produced spectral emissions that could be analyzed to determine chemical composition, temperature, and velocity. The fragments carried elements forged in the star's core, carbon, oxygen, iron, and distributed them across space, enriching the interstellar medium. In this way, the escaped star became part of the cosmic cycle of matter, contributing to the formation of new stars, planets, and potentially life itself. The speed and energy of the fragments created phenomena rarely observed. As the plasma moved through interstellar magnetic fields, it generated synchrotron radiation, a type of electromagnetic emission produced when charged particles spiral along magnetic lines at relativistic speeds. This radiation illuminated otherwise invisible regions, allowing astronomers to see structures that had previously been hidden. The star's escape had thus become a beacon, revealing the hidden architecture of the galaxy while continuing its own journey of survival. From a human perspective, the implications were profound. By observing the star's journey, scientists could probe the limits of astrophysical theory, studying tidal disruption, relativistic motion, and the interaction between matter and magnetic fields in extreme conditions. The fragments were a living laboratory, traveling through space and time, providing data impossible to replicate on Earth. Each photon, each collision, each arc of light contributed to a growing understanding of the universe's most violent and beautiful processes. Yet beyond science, the narrative carried a philosophical resonance. The star's survival against the overwhelming forces of a black hole was a cosmic story of resilience. In a region where matter should have been annihilated, fragments endured, traveled, and influenced their environment. They became agents of change, of creation, and of light in the darkness. This journey was not merely physical. It was symbolic, a reminder that even in the most hostile conditions, survival, transformation, and influence are possible. The fragments' interactions with galaxies beyond their own added another layer of complexity. As they traveled at extraordinary speeds, some fragments were eventually captured by the gravitational fields of neighboring galaxies. Their high-energy impacts could trigger new star formation, seed interstellar clouds with heavy elements, or modify the motion of interstellar gas. Over billions of years, the escaped star's influence would ripple across multiple galactic systems, a subtle but persistent testament to the enduring consequences of a single extraordinary event. Meanwhile, the radiation from the fragments continued to traverse space, reaching potential observers in distant systems. Any advanced civilization with the capability to detect high-energy emissions could witness the echoes of this cosmic drama, reconstructing the story of survival, energy, and defiance. The star, though physically fragmented, had left an imprint not only on the galaxy, but also on the perception of the universe itself, serving as a cosmic storyteller, sending data and light across unimaginable distances. The journey also illustrated the interplay between chaos and order in the cosmos. The escape of matter from the black hole, the interactions with interstellar clouds, the bending along magnetic fields, and the eventual seeding of new regions all demonstrated how energy and matter respond dynamically to extreme forces. Even in apparent randomness, there was structure, a cosmic choreography dictated by gravity, magnetism, and the fundamental laws of physics. The fragments were both chaotic and ordered, destructive and creative, a perfect illustration of the duality inherent in the universe. As the millennia passed, the escaped fragments continued to journey across the galaxy, a glowing testament to the forces that had propelled them. They interacted with dark matter halos, passed through regions of intense radiation, and occasionally collided with slower-moving interstellar particles, transferring energy and leaving traces detectable across vast distances. The star's story became a living thread woven into the galaxy's fabric, demonstrating the persistence of matter and energy even in the face of annihilation. The narrative of the escaped star also highlighted the importance of observation. Without telescopes, satellites, and spectroscopic instruments, this journey would remain invisible to human understanding. But through careful study, astronomers could map its trajectory, measure its velocity, and even predict future interactions with clouds, stars, and planetary systems. Every observation added to the collective knowledge of the universe, revealing both the complexity of extreme astrophysical processes and the beauty inherent in cosmic resilience. In essence, the fragments were more than matter. They were cosmic storytellers, carriers of energy and history, traveling across space to narrate an epic of survival, energy, and transformation. Their path illuminated the galaxy, enriched the interstellar medium, and provided a living laboratory for future generations of astronomers. The escaped star had become not just an object of observation, but a symbol of the extraordinary possibilities inherent in the universe. Over millions of years, the fragments of the star continued their incredible journey through interstellar space, moving far beyond the gravitational influence of the black hole that had nearly consumed them. The sheer speed of 8 million kilometers per hour allowed them to traverse vast stretches of the galaxy in what, by cosmic standards, was a brief moment. They carried with them not just matter, but a record of extreme forces, nuclear reactions, and energy flows, an interstellar memoir etched in plasma and light. Each fragment, ionized and radiant, became a beacon that illuminated regions of space otherwise shrouded in darkness. As the fragments traveled, they inevitably encountered other stellar systems. Some grazed the outskirts of stars, depositing high-energy particles into planetary atmospheres or interacting with circumstellar gas clouds. These interactions, though subtle, had the potential to influence the formation of planets, the evolution of atmospheres, and even the early chemical composition of emerging solar systems. The star's journey became a cosmic agent of influence, spreading material and energy across the galaxy, shaping environments far removed from its original system. Clouds of interstellar gas, nebulae, responded dynamically to the passage of the fragments. When high-velocity plasma collided with these clouds, shockwaves compressed the gas, sometimes igniting regions of new star formation. Regions of hydrogen and helium, once quiescent, glowed as they were energized by the fragments' kinetic energy and radiation. The star's remnants became catalysts for creation, transforming destruction into renewal. In this way, the legacy of a single star that narrowly escaped annihilation could ripple across the galaxy, influencing cosmic evolution for eons to come. Galactic magnetic fields added an additional layer of complexity to the star's path. Charged plasma followed the twists and spirals of magnetic field lines, creating luminous arcs and complex filamentary structures. These interactions illuminated the invisible architecture of the galaxy, revealing how energy, matter, and magnetism intertwine on scales beyond ordinary perception. The escaping fragments effectively mapped out the invisible forces of the galaxy, leaving behind trails of radiation and light that could be detected and studied by future civilizations. Over the course of billions of years, the star's fragments traveled even beyond their home galaxy. Gravity from neighboring galaxies occasionally redirected the fastest-moving material, capturing some fragments and integrating them into distant galactic environments. In these far-off regions, the material contributed to star formation, enriched interstellar gas with heavy elements, and subtly influenced the evolution of entirely separate stellar populations. The escape of a single star had ramifications that extended across galactic boundaries, demonstrating the interconnectedness of matter and energy on the largest scales. Radiation emitted by the fragments propagated even further than the matter itself. Photons traveling at the speed of light radiated through the cosmos, carrying information about the star's composition, velocity, and interactions with other matter. Advanced civilizations, equipped with sensitive instruments, could detect these emissions, reconstruct the event, and learn about physics occurring at energies and scales unimaginable on their own planets. The escaped star had become a universal messenger, a cosmic historian sending data across the galaxy and beyond. From a scientific standpoint, the implications were profound. Observing such high-velocity stellar remnants provides insight into relativistic physics, tidal disruption events, and the limits of matter under extreme conditions. Each measurement of velocity, radiation, and chemical composition helps refine models of black hole interactions and the behavior of matter near singularities. The star's escape also sheds light on the distribution of heavy elements throughout galaxies, showing how rare events contribute to the chemical evolution of the cosmos. Even as billions of years passed, the fragments continued to influence their surroundings. They collided with cosmic dust, energized gas clouds, and contributed to the formation of new stars and planetary systems. Some fragments, traveling through less dense regions of intergalactic space, remained virtually undisturbed, silent witnesses to the vast scales of time and space. Their journey became an enduring story, a narrative encoded in energy, matter, and light, a story that would persist long after the original star's life had ended. The escaped star also illustrated the profound interplay between destruction and creation in the universe. A star that was nearly obliterated by a black hole transformed into a source of energy, light, and matter that enriched its surroundings. This duality, catastrophe giving rise to creation, reflects the fundamental rhythms of cosmic evolution. In this sense, the universe is not merely a collection of objects obeying physical laws. It is a dynamic system where even extreme events have the power to shape structure, chemistry, and energy flow across unimaginable scales. From a philosophical perspective, the star's journey is a story of resilience and persistence. In the vicinity of the black hole, where space itself was twisted and time nearly halted, a fragment of matter survived. It traveled across interstellar and intergalactic space, enduring collisions, radiation, and the subtle gravitational influence of countless celestial bodies. The star's fragments became a symbol of defiance against oblivion, a demonstration that energy and matter can endure and continue to influence the cosmos despite the most extreme forces. The narrative of the escaping star also highlights the importance of observation and understanding. Through telescopes, satellites, and advanced spectroscopic instruments, humanity and potentially other civilizations can witness these phenomena, reconstruct the history of the escape, and study the physics behind it. Every photon, every collision, every arc of light tells a story of forces, energy, and survival that contributes to a deeper comprehension of the universe. The star, in its flight, became both a natural laboratory and a cosmic storyteller. Even now, as the fragments travel across eons and light years, their influence continues. They will collide with clouds of gas, contribute to the enrichment of new stars, and interact with magnetic fields and cosmic radiation. Their journey is not finite. It is a continuous process of interaction, transformation, and influence that will persist as long as the galaxy exists. The 8 million km/h escape is not merely a moment of defiance. It is an ongoing legacy, a phenomenon whose effects will reverberate across space and time for billions of years. The star's journey teaches us something profound about the universe. Even in the face of overwhelming force, persistence is possible. Light, energy, and matter can endure, travel, and transform their environment in ways that ripple across unimaginable distances. The story of the star that escaped a black hole is not only a scientific marvel, it is a cosmic narrative of resilience, persistence, and transformation, a tale that continues to unfold as the fragments race through space, illuminating the galaxy and inspiring generations of observers. As the fragments of the escaped star surged onward, they eventually left the confines of their home galaxy, entering the vast emptiness of intergalactic space. This region, far from the dense clusters of stars and nebulae, seemed almost desolate. But even here, the star's fragments carried energy, momentum, and information, interacting subtly with the cosmic environment. Collisions with sparse hydrogen clouds created faint flashes of radiation, and magnetic fields, though weaker than within a galaxy, still guided streams of charged plasma along invisible paths. The star's remnants were no longer bound to any single galaxy. They were wanderers of the cosmos, emissaries of light and matter, traveling across unimaginable distances. The intergalactic medium, while extremely diffuse, was not empty. Traces of primordial gas, cosmic dust, and dark matter pervaded the space between galaxies. As the star's fragments moved through this environment, they subtly influenced its dynamics. Energetic collisions ionized neutral gas, creating transient luminous trails detectable to advanced civilizations far from the star's origin. Even in this sparsely populated space, the escaped star continued to impact its surroundings, a living demonstration of the principle that matter and energy cannot be fully confined or destroyed. They persist, transform, and propagate through the universe. For observers within countless light years, the star's journey offered both spectacle and knowledge. Instruments capable of detecting high-energy emissions could reconstruct the velocity, trajectory, and composition of the fragments. Each photon, traveling across eons, carried encoded information about the forces that had propelled the star from annihilation to survival. Advanced civilizations, studying these cosmic signals, might uncover the extraordinary story, gaining insights into black hole physics, relativistic motion, and the ultimate resilience of matter under extreme conditions. In this way, the escaped star became a universal messenger, a record of cosmic history traveling faster than time itself, in human terms. Over billions of years, the fragment's influence extended beyond immediate interactions. As some collided with isolated interstellar clouds, they enriched these regions with heavier elements forged in the star's core: carbon, oxygen, iron, providing the chemical foundation for future stars, planets, and even life. The process of seeding matter across space is fundamental to cosmic evolution, demonstrating how the violent death, or near death, of a single star can have consequences spanning galaxies. From this perspective, the star's escape was not merely an act of survival, but a catalyst for creation, transformation, and renewal on a universal scale. Meanwhile, radiation from the fragments continued to propagate at the speed of light, reaching distant systems long before the matter itself. Gamma rays, X-rays, and visible light formed a luminous wake that illuminated the otherwise invisible intergalactic medium. This radiation carried not only energy, but also data: fingerprints of atomic transitions, Doppler shifts indicating velocity, and polarization patterns revealing magnetic field interactions. Observing civilizations could, in principle, reconstruct the entire event, mapping the escape, the tidal disruption, and the plasma dynamics in remarkable detail. The star's story, though originating billions of years ago, became timeless, transmitted across the universe via light and energy. From a philosophical standpoint, the star's journey is a testament to resilience and persistence in the cosmos. In the immediate vicinity of a black hole, where matter is generally thought to vanish forever, fragments endured and continued to influence the universe. The persistence of matter and energy, even under extreme forces, highlights the universe's inherent potential for survival and transformation. The star's escape demonstrates that in a cosmos defined by gravity, radiation, and entropy, there are moments when order and creativity emerge from apparent chaos. The long-term fate of the fragments also illustrates the interplay between chaos and order on cosmic scales. While collisions with gas clouds and magnetic interactions appear chaotic, they follow predictable physical laws. Energy and matter are conserved, forces propagate according to universal principles, and outcomes, while complex, are governed by the interactions of fundamental particles and fields. The star's escape embodies this duality: a chaotic event that produces orderly consequences, destruction that seeds creation, and violence that fosters beauty. Over time, as the fragments drifted ever farther, they became integrated into the ongoing cosmic web. Some merged with nascent stars, contributing material that would shape future generations of stellar bodies. Others added energy to interstellar and intergalactic magnetic fields, subtly influencing galactic evolution. The escaped star's influence, though originating from a singular and violent event, radiated across eons, connecting disparate regions of space through the fundamental processes of matter, energy, and gravity. In this way, the star's legacy became woven into the universe itself, a story not confined to a single moment, but continuing across time and space. The escaped star also illustrates the nature of observation and discovery. Humanity and hypothetical advanced civilizations can witness its effects, measure its energy, and understand the physics behind it, even billions of years after the initial encounter. Each observation becomes a bridge between events separated by vast stretches of space and time, connecting sentient beings with the distant past. The star, though fragmented and scattered, continues to communicate with the universe, telling a story of survival, energy, and cosmic resilience. Ultimately, the narrative of the star that escaped a black hole at 8 million kilometers per hour is more than a scientific account. It is a cosmic epic. It is a story of survival against overwhelming odds, of energy persisting through destruction, and of matter shaping the universe long after the original star's life had ended. Its journey encompasses the extremes of physics, the intricacies of galactic dynamics, and the enduring beauty of cosmic processes. The star's fragments continue to illuminate space, enrich matter, and travel across galaxies, serving as a testament to the resilience inherent in the universe itself. In conclusion, the escaped star stands as a symbol of the universe's extraordinary capacity for resilience, transformation, and persistence. From a moment it nearly fell into oblivion to its ongoing journey across interstellar and intergalactic space, it embodies the interplay between destruction and creation, chaos and order, darkness and light. Its story, carried by matter and radiation, endures across billions of years and unimaginable distances, offering both knowledge and inspiration to any who observe it. The universe, in allowing this escape, demonstrates that even in the face of overwhelming force, energy can survive, matter can endure, and light can persist, leaving a legacy that stretches across the cosmos and into eternity.